Hello and welcome to this video. And in this video I'm going to show you how you could use the wave function collab nodes in Houdini. So before I get started, maybe just quickly let you know what this wave function collapse is. So here are some examples of what it can do. So this is here our input image, and it will then generate these other outputs. So here are more examples of this. So we can use a basic image that we can create ourselves, and then we can use this algorithm to then make it bigger and expand on it. Now, if you're interested in learning more about this, I can recommend you going to this GitHub, and there's a lot of documentation here on how you can use it and what it is exactly. Now, going to Houdini, let's create a geometry network. So in here, let's start creating some of these wave function collab nodes. So if you have installed the lab tools, you can see these nodes. So I'm going to start out with the initialize node. So you will see this grid made out of points. So if I would enable points, we have this as result. So we can set a custom row and columns. You can also override what you see, like you can make a selection like this, press enter, and then you have this as a new selection. And you can give it a custom names, like here, just gonna give it name. You can, for example, name this is a wall, then you do another selection for a door, and so on. But what is mainly interested in here is that we can actually use a texture. So I'm gonna load in a texture, like this one here, for example. So important to know is that each pixel would then be one point or a dot. So be sure to keep like low resolution. So in this case, it's like 20 by 20. So now let's use this. So this is then my main pattern. And I want to use this then with the wave function collapse node. So this is sort of the solver or where calculation will happen. And I need another initialize grid. And this is then the grid that decides how large my output will be. So let's say if I want to have a 30 by 30 grid as output, so it's a larger one, then this is then my grid. So this is the first input, and the second input is then the sample grid or the grid with the pattern. So just by default, it will already create this over here. As you can see, it will generate this for you. So now in here we have our settings, and here we have our main search radius, which is in this case 3. So that means that if I would go to my original grid, it will look in a radius of 3 by 3. So if you lower this, it would be 2 by 2 or 1. So as you can see, if you would do this 2 by 2, it's getting a bit random. If you just use 1, it's getting very random. So most of the time 3 is a very good value to get still some structure. If you want some randomness, 2 can be useful in here. Then also we have here the find wrapping input patterns. We can enable this. If this toggle is on, it considers the pixel on the border on the right side of the sample to be a neighbor of the pixel on the left side of the border. So when we have a search radius 3 by 3, it will look on the right side and on the left side to be able to be wrapping. So for our output, the most right pixel is allowed to be placed next to the most left pixel. So they are able to be wrapping based on, of course, our pattern over here. Then we also have here the option for allow rotations. When it is solving the wave function collapse, it is also going to allow the patterns to be rotated. This will also help against repeatable areas. Then we also here have respect user provided constraint. This means that in here, in our first input, if we would set up, for example, here a constraint or some predefined points. So in this case, I'm going to make sure the value that I'm setting here is 111. And this can be found with our main pattern. So if I would go over here, I have here names that are either 000 or 111. So they have to be the same value. So that means that in here, these 2 points will always be 111 value. To make this more clear, I also added a box here for visualization. And when I enable this, you will now see that these points are going to be consistently the same value. So if I would play around here with the seed, they will always be respecting the constraint. Now, something very important here with this provided constraints, that we cannot just randomly select points. So if I would go here and would say, oh yeah, I want these to be a certain room, and press enter, it will throw an error at us. What you could do is you can go into advanced. You have here an option to increase the attempts to solve it, so you can increase this, but this will probably keep failing. So the reason here is it's going to find a link between this input and our main pattern. So you need to keep that in mind, that we cannot just randomly select points in here, because it's going to find a link with a search radius to my pattern over here. So if it cannot find any link, so it will just throw that warning. So you're going to have to keep that in mind. So most of the time, just selecting a few points will do, but if you're going to for some more complex shapes, then it will be more difficult, because again, it needs to be able to find what you're selecting also in your main pattern that you're inputting. So but this can be very useful to override certain positions. Like if you want to have a certain door somewhere, you can just select where you want to have a door and it will be overridden. Then further here we have a setting for produce tileable outputs. So if you want the output to be tileable, so we can click this, then you can see that these are tiling. Then we have further here the seed value, so this would just get variations in here. So very useful to get quickly variation on a level layout or a city, whatever you want to use this function for. Then we have here further use observant sample frequency, so we can enable this as well. And you can see that it changes a lot of things in here. So what this does, it's sort of getting the frequency of pattern founds, and it's going to take that in account when creating a new output. So it's going to look at the main pattern here, and it's going to take in account the ratio between how many white and how many black values we have. And it's going to try to translate that into our new solved pattern. So it can be very useful also if you're working with colors to sort of keep the same ratio as your input image. So if you would have, for example, have like around 10% red dots, then it would still try to respect that option of 10% are red dots. So by enabling this frequency, it's trying to match these amounts. So if you were not enabling this, it's not really caring about these frequencies found in patterns. Then further here we have number of solving attempts. So in some cases, when you enable some settings, you might be able to increase the number of solves. So if you're using the respect user provide constraint, this can be very useful to, for example, increase the number of solves, because sometimes it needs just a bit more attempts to solve it completely. Then we also have here the last setting is called start point. We can decide where we want to start with solving this pattern. So otherwise it's going to be in a bit more random way, and in here we can say a very specific point where I want this to be solved. So this can be useful sometimes when you're working with provided constraints, or in another situation where you want to maybe need a specific point to then start with. Now further I want to use this as a result to then make, for example, a level. Now what's working really well with the wave function collab tiles is the Wang tile samples. So in Houdini we also have a Wang tile, so we have the decoder and the sample one. So I will first use the sample one for demonstration. And I will click here align and distribute. And these are all pieces, like a corner piece or a piece with a pillar. And we can use the Wang algorithm to then automatically figure out where to place all these tiles based on here our pattern. Useful to know when you're working with these Wang tiles is here we have the blob tile set. So each piece has its number. So when there is nothing, it's number 0. When there is something, we have, for example, here number 1, and then the other variations over here are the rotated versions. So all of these numbers are representing the tile set. So if I would go over here to the WoW samples, we can see that the names over here are actually the number of the tile set. So it's very useful. Now let's use now the Wang decoder, and you will see here it's using this blob tile set, so that's from the image that I just showed you with the numbers. Then it's going to look based on colors. So you're going to have to make sure we have colors stored in points. So be sure to double check your point information if they have any color information. So in my case they have. So it's going to look at the red channel, and I also want to check that the rows and columns are the same as my input. So in here I use 30, so I'm going to here use 30 by 30 as well. Now we need to combine these two with a copy to points. So plug in the geometry here and then the pattern over here. So just by now it will just plug in all the tiles on these points, but that's not really what I want. I want to use here the piece attribute and type in here name. And now I have the result that I want to. So now it makes all these rooms based on these tile sets. So this is all done for you. So this is a really quick way of getting a basic layout for a level, for example. And then we can go here, play around with the seed, and you can see that everything just changes along when I change the seed. If you're working with an artist, you can just here align and distribute and, for example, export this. So you can use exporting node and export this and give this style set to an artist, and he can then modify all these styles to then fit what your game is. Now something else we have not talked about with the VFC is the other node which is called sample paint. So I'm going to place it here. So the first input will be a grid. So let's use the grid. And here I'm going to keep it 20 by 20, plug it in over here. And we have a second input called modules. So these are actually models. So this can be anything. If you have a model for pipes, you can then plug in all your modular pipes. If you have model for houses, you can plug in all the house models. But in this case, I want to use the Wang tile samples. So I'm going to plug in here. So again, these are just geometry. So you can plug in everything you want. And in this node itself, in the paint, we're going to click here on initialize value mapping. So click on this and it will automatically look for all the models that are available. So in this case, there are 47 objects, which is representing, of course, all the tiles. So now with the paint tool, we can then paint these models. So we're going to have to switch to this handle over here. And when we scroll with the mouse, you can see that we can actually start painting models. So I can click on where I want a model and start painting them. And this way we can then quickly block out a level that you want to as well. But again, here you can also use different models. So in this case, I just took the sample files because I had them laying around. But you might as well use different options. Like if you have models for a pipe, you can then, for example, draw your pipes here, and then you can plug this in still over here. So let's just, for example, copy this, and you can use this in here as well, and then continue with the wave function collapse. So it will generate a new pattern for you based on what you have painted here. Instead of painting an image in another software, we can then actually here paint with our 3D models that are available to what you want. So this was the first video of the wave function collapse videos. I hope you enjoyed it, and thank you for watching.